Hey y'all, there were some concerns that the full working solutions were not shown on the key for assignment number 4. So in this video, I'm going to fill in some of those gaps a little bit. Rather than typing it up and redistributing it, I'm going to make a video and I'm going to include some explanations. I'm not going to be doing every exercise because, well, for starters, that would be an extremely long and boring video. But I don't think you probably need all of them. I can help you with some of them, and then in class, I'm sharing what all the U values are in case that's something that you need for further support. So without further ado, I'm going to just pick a few of them and we are going to run through them, and hopefully that will be helpful to you. So I think I'll start with number 2. And number 2 goes like this. And I've got a 3x, or 3 minus x to the 10th dx. And I'm going to add in a couple stuff that I'm noticing in class that we're missing. So pay attention not only to what I'm writing, but also the stuff I say. So the first thing that I notice is some of you are not writing down the dx, especially when you make the sub. You have to do that. Guys, that's the same idea as why d dx means that we're going to take a derivative. The d is saying a derivative. The dx is saying with respect to x. The integrand right here is saying that we need to do an antiderivative or an integral, and the dx is saying with respect to x. And I know it might not feel like that matters that much yet, especially if you're going on to science or engineering. It's really going to matter in about a year when you take multivariable calculus. You'll actually see why if you don't do this, it'll cause you a lot of distress. So I'm going to start picking my u now, and I'm going to start making my sub here. So there's really only 3 or 4 steps. First step is pick your u value. The thing that I'm noticing in class is a lot of people are picking too much, like they're picking 3 minus x to the 10th. And that's going to cause a problem when you take a derivative because you're going to need a chain rule. So let's not do that. Let's pick less, 3 minus x. I saw a lot of you were writing du, but when I talked to you, a lot of you didn't realize what that was. When we go from here to here, what we're doing is we're actually taking a derivative. So when I take the derivative of 3 minus x, what I get is negative 1. And then remember, when we're taking a derivative with respect to x, in a u sub, we're always going to write dx right there. So now we're going to go ahead and make our substitution. And so the whole point of that is we're going to try to make this nasty thing over here look a little bit easier by writing an equivalent expression that's easier to work with. So instead of 3 minus x, we're going to write u. So now we've got u to the 10th. That's something we know how to work with. I've got a dx right here, and I've got a dx right there, but I have that negative 1 in the way. So what I'm going to do is I'm going to divide out the negative 1. And so now when I do that, I'm going to come over here. Those cross out. Instead of dx, I'm going to write du over negative 1. And so what I was showing in the video previously is I'd factor that out to the front. So dividing by negative 1, multiplying by negative 1, those are equivalent. So I'm going to bring a minus out here. That now gives me u to the 10th du. Now, one of the mistakes that I saw a lot of you making in class is you'd then sub it back. You'd go ahead and put in the 3 minus x back. The problem with that is that undoes the work we just did and takes us exactly back to where we started. And that's not good. We don't want to undo our work. We want to progress forward. So let's think about what the steps to this are. We define u. We take a derivative to find du. We make our substitution. Then we need to actually find the antiderivative. So add and divide. Add 1. That'd be divided by 11. And so now we're going to rewrite what we have. When I actually do this right here, when I do the add and divide, that's what kills off my integrand in my du because I've completed the command. I've done what I was asked. So I'm not going to rewrite those. So now I've got negative u to the 11th over 11 plus c. This is the part where I'm going to sub it back in now that I've actually done the calculus. Once the calculus is done, now I'm going to substitute backward again. So I get negative 3 minus x to the 11th over 11 plus c. Okay, so I'm going to pick up the pace a little bit as I go here, and I'm going to try to pick off some of what look like maybe the more challenging problems as I go, and we'll just do a couple of them here. So maybe we can try number 5. I saw some people struggling with that a little bit in class the other day. So e to the 5x plus 2, excuse me, I'm fumbling with my new pen here just a little bit, so give me just a second. 5x plus 2. Yep, it's got all kinds of buttons, and I don't actually know what all of them do, and sometimes I hit them on accident. So sorry about that, guys. So then a dx. All right, and so I've got a function. I've got another function. I'm going to take that one that's written smaller, think like the inside nesting doll in a chain rule. So u equals 5x minus 2. Taking a derivative of that, du, derivative of 5x minus 2 is 5, and I get a dx right there. And so now it's substitution time. So I get e to the u. I need something to plug in instead of dx, and guys, that's why it's really important you write it. So there's my dx. I want to isolate that. So divide by 5. And now I have dx equals du over 5. So du over 5. For my money, it's harder to understand that. So and that's a multiplied constant. We can always take multiplied constants and factor them out to the front. So 1/5. I'm going to scratch that out. And then remember, if you had a derivative of e to the u, you would write e to the u. It is its own derivative, okay? And those variables match, so it isn't actually a chain rule. Or I guess it is, but then the derivative of u in this case, because it's with respect to u, derivative of u would be 1. So what we do is we keep the 1/5. It's still e to the u plus c, and then we're going to make our sub back again. So we have 1/5 e to the 5x minus 2. Now, if that's confusing to you, check your answer. Take a derivative of it. I'm switching colors here so you can see. How would you take a derivative of this little guy right here? Well, and I'm going to put a little check. We're checking our work. And that's supposed to be an arrow. Okay, so the way we check our work is we rewrite what we see. So e to the 5x minus 2. So writing what we see, and then we'd also take the derivative of the exponent, or the dog as we call it, derivative of the guts, and we'd multiply that down in front. So derivative of 5x minus 2 is 5, so that would bring a little 5 right here. Those would cancel, and notice that's the original question again up here. So we've checked our work now. We should feel really, really comfortable that that's right. Okay. The next one that looks really interesting is number 7. Number 7 looks pretty exciting, so let's try that. All right, and I get sine of natural log of x, and don't forget all your parentheses, over x dx. Holy moly. Okay, that looks a little intimidating, so let's attack it. I want to demonstrate here, and guys, I hope you're listening to what I'm saying as well as what I'm doing. I actually want to demonstrate what happens if you get it wrong, okay? And what I mean is if you get u wrong. So some people look at this and go, oh man, that's scary. I'm just going to call you sine of ln of x. Okay, and I want to show you how you'd know if you had the right u or the wrong u. So if you have the wrong u, here's what's going to happen. You're going to start taking a derivative of this. And you need to remember that's a chain rule. So guys, that's one of the challenges with integrals. We have to remember all of our derivative rules. So the sine turns into cosine. What happens to the guts? The guts stay the same, ln x. And then we multiply by the derivative of the guts, which is 1 over x. And so here's how you'd know that this is wrong. Because when you go to plug in this u, instead of sine ln x, you get a u right there. The only stuff that's left over is an x and a dx. But you see how much junk there is down here? There's tons of stuff. There's no cosine in this equation. So there's far too much information in our du, way more than we can deal with. Now, if there's not enough information in the du, that's okay. I'm going to teach you how to deal with that in a few minutes. But if you have too much information, there's something wrong, and you're not going to be able to fix that. So what we need to do is actually go back and pick a different value for u then instead. So let's do that. I want to pick a little bit less. That was too much of a value, and I don't mean too large numerically, but I mean there was too much complexity in the u. So I'm going to try something a little bit less. I'm going to try natural log of x. And so we need to remember our derivative rules. So du equals 1 over x, and there's a dx, and some people have a hard time understanding how that's going to work. So guys, I'm going to show you one little trick when you have a fraction like this. One thing you can do is you can start with by writing the numerator, sine of natural log of x, multiplied by 1 over x dx. And the reason I'm writing it this way is I want it to be a little easier for you to see what's going on. So maybe now you can see that I've got my ln x right there, so that's going to match, and I've got my 1 over x dx sitting right there, and notice it's the same thing. There's an x on the bottom, this 1 would multiply in, and so yeah, these two expressions are equivalent. I haven't made a substitution, I'm just doing a little bit of rearranging to help you see what I'm about to do and make sure you can understand it. So now that I have that, I'm ready to make a substitution. And so here I go. Some people get a little bit uncomfortable here because the sine doesn't go away. Guys, that's not a problem. We know how to integrate sine, so that shouldn't be stressful. ln x turns to u, so we get sine of u. 1 over x dx, 1 over x dx, that turns to du. And so now we have successfully taken something that looks pretty darn challenging, a bunch of nested functions and ratios, and we have turned that into integral of sine. Okay, so no big deal, right? So integral of sine, do you remember what that is? It should be negative cosine. Okay, so negative cosine of u plus c. Now let's make our substitution backward. And so what do we get? Negative cosine, I'm going to go to a new line, I'm running out of space. Negative cosine of natural log of x plus c. And that's it. Okay, so it's the same steps we've been doing all day. Okay, we start with our function. We find u, take a derivative, sub it in, antiderivatize, and then resub back so you end with something that has x in it, not with u. Because the question was asked in x, so we need to answer in x. Now that gets a little bit confusing for a lot of people, and guys, some of you have expressed this to me, because sometimes we don't sub it back in. So let's find an example where that happens, and let's try to understand that a little bit better. Maybe a good example would be something like number 11, so you can understand what I'm talking about when I say that. Okay, number 11 goes like this. So we have bounds now, 0 to 7, that's 11, not multiplied, question number 11. Root of 4 plus 3x dx. I'm going to pick my u is 4 plus 3x. My du is going to be the derivative of that, so 3 dx. And let's start thinking about making substitutions. So here I go. I'm not going to write root. What I'm going to instead write is the 1/2 power, because that's going to be a little bit more calculusable. So 4 plus 3x, that would turn into u, and it's going to be to the 1/2 power, and that looks pretty friendly. I have a dx right here. I have a dx right there. There's a 3 in the way, so by 3, go away. And so now I have a du over 3, and I showed this trick in the first example. I'm going to put a du there and a 1/3 here, and the only thing I've forgotten is the bounds. And so remember, the way we get those is we plug these bounds, because those are x values, because that says x. And based on the fact that that's a u, these now need to be u values. So we need to turn these x values into u values. How do we do that? We have an equation right here that tells us how to turn x into u. So that's what we're going to do. I'm going to plug a 0 in here, and y'all, I'm doing mental math on this. When I plug in a 0 right here, 0 times 3 is 0, plus 4 is 4. So that's how I'm getting that. I plug a 7 in here, and I get 21 plus 4. What is 21 plus 4? That's 25. And so now we're all set. We're ready to go. So let's get an antiderivative. Remember, add and divide. Okay, and so 1/2 plus 1 is 3/2. I'm going to flip that and multiply, so I'm doing 2 steps in one here. So I have my 1/3, that's from out here. I'm going to flip this and multiply, so that becomes 2/3. I have u to the 3/2 power, and don't forget your bounds. So 25 and 4. And so now let's do some simplifying. Looks like I have 2/9. And I'm going to apply the fundamental theorem of calculus. Now, guys, this is where some people have been switching back to x. Please don't do that. We've worked really hard to switch to u. When you see bounds, your answer is going to be a number. And when we get a number out, it doesn't know if this was x or u. I mean, these are u values. We switched them. So we're just doing extra work if we switch it back. Let's go ahead and plug this in. So we'll write out 25 to the 3/2 minus 4 to the 3/2. Let's pause for a second and make sure we understand what the 3/2 power is. X to the 3/2 is the same thing as x cubed with a square root. So with that in mind, let's simplify this out. So I've got 2/9. When you take 25 to the 3/2 or 25 square root and cubed, it doesn't matter if you square root or cube it first. I noticed 25 and 4, it's really easy to square root them, so that's what I'm going to do first. And guys, I'm just doing mental math here. Square root of 25 is 5. 5 cubed is 125. Going over here, square root of 4 is 2. 2 cubed is 8. So 125 minus 8. Okay, and I'm not going to show the rest of the steps. I'm going to assume you can simplify that on the key. It says 26, and that's the key that I made earlier. If there's a mistake on it, show me in class and we'll get it fixed, okay? I want to show one more to you. There's one more thing that can happen that can get a little bit stressful for some people at times, and that happens in number 16. And so let's take a look at that. So in number 16, we have a definite integral. We have bounds, 0 to 4, and we have an x on top and a root of 1 plus 2x on the bottom. Now that doesn't necessarily look as scary as some of the stuff we've already done. It doesn't have logarithms inside of trig functions or anything like that. I mean, it looks relatively straightforward, but a lot of times this can be a wolf in sheep's clothes, so to speak. So what I mean is that a lot of times in math, the stuff that looks really, really hard isn't so bad, but sometimes the stuff that looks more benign like this can be a little bit treacherous. So let's walk through it. First thing we need to do is we need to pick our value of u. I'm going to pick 1 plus 2x, and because I don't mean that I'm picking it arbitrarily, I mean that this is what it has to be. I think you'll see why in just a second. So then our du, if we do that, is 2 dx, remember, taking a derivative. And now we're going to try to make a substitution. So let's see what happens when we do that. So I know there's a fraction. There's a root on the bottom. 1 plus 2x turns into u. And so I've dealt with that. I have a dx here. And so I need to deal with that somehow, but there's no 2 in here. So I'm going to dish out the 2 to the other side. Cancel that out. And so I get a du over 2. But there's a little bit of an issue. Okay, we've accounted for the root in the 1 plus 2x. We've accounted for the dx. It's right there. We have in no way accounted for the x. And so a lot of people get stuck here and they get really, really frustrated. Now, when we did the example that was sine of natural log of x divided by x, I said one of the ways we know if our u is wrong is if we have too much information. We don't have too much information here. We were able to use this perfectly. And so that indicates to us that probably this is still going to work. There's probably still a creative way to do this. We didn't have extra information. We actually don't have enough information to get rid of this, or at least that's what it looks like right now. So here's the trick. We need to manipulate one of these expressions in our little cloud so that they look like this. So what will that be? Well, let's see. This is the only thing right here that has an x. And so what I'm going to do is I'm going to bring this down and try to isolate it. So I'm going to rewrite this as u minus 1 equals 2x, and we'll divide that by 2. And so I get, oops, make it look like a 2, Mr. B. And so that says u minus 1 over 2 equals x. And so now we have an expression for x. And so in here, I'm going to put u minus 1 over 2. And you go, but wait a minute, that looks horrible. Yeah, y'all, I get that. That looks a little scary. Triple stack your fractions are only good at Wendy's and when it's on a burger. But there's a pretty simple trick to deal with this, so we'll do that in just a second. We do need to switch our bounds into u, so let's do that. Plug a 0 into here, and you get out a 1. Plug a 4 into here, and you get out a 9. Okay, so we've switched our bounds, and we're ready to simplify, so let's get on with it. Okay, so here's what I want to do. I want you to think of this. I'm going to leave the 1 and the 9. I want you to think of this as 1/2 multiplied by u minus 1 divided by u to the 1/2 power. And I'm going to pull this 2 out in front right now, so I'm going to have a 1/2, and then du is just going to be du. It's not going to have the 1/2 anymore. And the reason I want you to see this is because I'm about to pull this 2 to the outside, which is this 2 right here. I'm about to pull it out. A lot of times if I don't write this here, people aren't able to see it. So I want you to pull this out. And also, roots are not very calculusable. Exponents are very calculusable, so that's why I'm doing that. And I'm going to box this off as kind of the secondary part of my cloud here so it doesn't get in our way. Okay, now I'm going to simplify. So I'm going to pull this out. So when I pull that out, I'm going to have a 1/2 and a 1/2. That's going to turn into 1/4. My bounds are still 1 and 9. I have not integrated yet, so please don't plug it in yet. I have not done an add and divide rule. I haven't done any e rules. I haven't done any log rules. So you're not plugging those in yet. We still have an integrand. We still have the bounds. I've got u minus 1 over u to the 1/2. And so it's starting to look a little better, and we're just going to kind of keep massaging this until it's workable. So here we go. I'm going to remember that that's u to the first, and do you remember what happens when we have u divided by u? What do we do with the exponents? We subtract them. So when I simplify that, what I now get, I have a 1 and a 4, and I have a 1/4. Excuse me, I was thinking of this 4. That's actually a 9 up there. Apologies. So I get u to the 1/2 when I do that. And what about this? This is 1 divided by u to the 1/2. Okay, there's a couple ways to think about it. Some of you can see we're just going to bring it up and write it as negative 1/2. If you're having trouble seeing that, you could think of 1 as u to the 0 power. Remember, anything to the 0 power is 1. So that would be 0 minus 1/2. That would be another explanation of why this turns into u to the negative 1/2. Okay, so now this is calculusable. Now we're going to actually do our antiderivative. And so here I go. So I have a 1/4 still. 4th. And u to the 1/2 becomes u to the 3/2. Remember, we're adding 1. and then I'm going to multiply by the reciprocal. So dividing by that or multiplying by the reciprocal is the same thing. So that becomes 2/3 minus, add 1, so that turns into a half. So u to the 1/2 dividing by the 1/2 is the same as multiplying by 2. And we still have our bounds, 9 and 1. So it's fundamental theorem of calculus time. We're going to plug those in. Now, I'm thinking you probably know how to plug those in already, so I'm not going to continue with the steps here because that would take probably 5 or 10 more minutes, and I don't know if it's going to be beneficial for you to watch me go through how to square root the numbers 9 and 1. I don't think that's going to help you. So I'm going to cut to the chase here. So then a miracle occurs, and 10/3 is the answer. Wonderful. Okay. So last thing I want to leave you with, guys, is maybe a little bit of a discussion about what the process looks like. So what do we do for the process? Because that's what I'm seeing that we're getting a little bit mixed up on. And so in order to think about the process, we probably need to think about two things. We need to think about definite integrals versus indefinite. And if you're not sure what I mean, a definite integral has bounds. And an indefinite has no bounds. Okay, what's the difference in the answer? In this one, the answer equals a number because we're going to end up applying the fundamental theorem, plugging in 2 and 4. The answer over here equals an expression. And it's going to have a plus c in it. Okay, so let's understand that first of all. And then what do we do in u subs? In u sub, what is our process? We pick u. Do we do that in both cases? Yeah, we do. We absolutely pick u in both cases. Next thing we do is we find du, or the derivative of that. So we're building our cloud. Okay, what next? We actually make a substitution. So sub in u and du. Awesome. That's the same whether it's definite or indefinite. Now we need to maybe simplify, but we're going to actually find the antiderivative. And here's where these two methods diverge. And this is what I'm seeing a lot of people get confused with. So if it's definite, then we're going to apply the fundamental theorem. So I'm going to break this up into two halves. So definite on the left. So once you found the antiderivative, it's fundamental theorem of calculus. Plug in your bounds. If it's indefinite, then sub u out. Or as some of you are saying, we're going to switch it back to x's. So that's because when you sub u out, that's going to lead to your answer being an expression with an x in it, with a plus c in it. If you use the fundamental theorem, then what you're going to get is you're going to get a number, because everything's going to simplify out and you're going to get a number. So guys, what I'm trying to do here is formalize this process for you a little bit, because I think we're getting a little bit confused. I don't know that you need to memorize it, but I want you to use this as a guide when you're practicing, because you're going to get the hang of this if you practice it enough. So pick u, find du, sub it in, antiderivatize, and then there's only one of two things this is the only place in the whole process you have a choice. You're going to do the fundamental theorem or sub, and actually, guys, it's really not a choice. All you're going to do is you're going to realize if it's definite, plug in the bounds. If it's not definite, if it's indefinite, then you can't plug in the bounds, so you're going to plug in u. Something gets plugged in. Is it a number or an expression? Is it a u expression or is it a number? Okay, so that's going to conclude this video for today. Keep talking to me, guys. I'm going to keep making videos when you tell me what you need. When you need more support, let me know, and I will continue to make this better and more functional for you. So that's all for now. Hope you enjoyed. Hope this is helpful for you, and I'll see you next time.